Hey everyone, and welcome to this explainer. I am absolutely thrilled to guide you through today's topic, because we're going to be looking at something truly fundamental. We're diving into the grammar of the universe itself, chemical reactions and equations. Now, if you think about it, chemistry isn't just, something that happens inside glass beakers in some distant sterile laboratory. It's actually a universal language. It explains literally everything happening around us, inside us, and across the entire cosmos. So by the end of this explainer, we're going to learn exactly how to read, write, and honestly, even balance the dynamic story of matter together. Let's get into it.
I want to kick off our journey with this brilliant quote from Martin H. Fisher. He said, "Facts are not science, as the dictionary is not literature." And man, that hits the nail on the head. It's so easy to think of chemistry as just this chore of memorizing a giant list of rigid formulas, right? But it's actually a living language. Just like words come together to tell a super captivating story, elements and compounds interact to create the dynamic, ever-changing world we actually live in. We aren't just memorizing here. We are learning how to read the ongoing story of matter.
Okay, so here's our roadmap for today. We'll start by figuring out how to spot a chemical reaction out in the wild. Then, we'll learn the actual syntax of equation language, we'll master balancing the scales of mass, and finally, we're going to explore both combination and decomposition reactions.
All right, moving right along to Section 1, Spotting Chemical Reactions, the Vocabulary of Change.
Think about these totally everyday situations for a second. What happens when milk is just left out at room temperature during a sweltering summer day? It goes bad, right? Or what about when an iron tava, a pan, or even just an iron nail is left exposed to a super humid atmosphere? It rusts. Think about grapes getting fermented, the food we cook for dinner, the food getting digested in our bellies right at this very moment. Or honestly, just the simple act of breathing in and out. In literally all of these situations, the nature and the actual identity of the initial substance have changed. They've undergone a chemical change, and whenever a chemical change occurs, we can definitively say, hey, a chemical reaction has just taken place.
But you might be wondering, if we're standing in a laboratory setting, or just observing something totally new, what is really meant by a chemical reaction? Or more importantly, how do we actually come to know that a chemical reaction has taken place? Like, what's the tangible, empirical evidence we need to look for with our own eyes?
Well, there are actually 4 key observations that help us definitively determine if a chemical reaction has occurred. We're looking for a change in state, a change in color, the evolution of a gas, and a change in temperature. Let's ground this in some classic textbook experiments. If you take a strip of magnesium ribbon, clean it up with some sandpaper, and then burn it, it burns with this absolutely dazzling white flame, and it physically changes into a white powder called magnesium oxide. That is a massive, dramatic visual change. Or, consider taking some zinc granules, dropping them in a conical flask, and adding dilute sulfuric or hydrochloric acid. Almost immediately you'll see bubbles forming. That's the evolution of hydrogen gas. And if you were to actually touch the outside of the flask, you'd feel a noticeable change in temperature. It gets hot. These 4 indicators are essentially the universe's way of telling us, hey, a chemical reaction is underway right now.
Which brings us to Section 2, the language of equations, writing the syntax.
So, describing a reaction in a full written sentence, like saying when a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide, is frankly just way too long. Scientists like to be efficient. The simplest way to shorten this whole thing down is by writing a word equation. The substances undergoing the change, which are magnesium and oxygen, are our reactants, and we link them with a plus sign. The brand new substance formed, magnesium oxide, is our product, and that little arrow, it just points toward the product, showing the direction of the reaction. Simple enough? But wait, we can make this even more concise by using actual chemical formulae instead of spelling out the words. Mg plus O2 yields MgO. This chemical equation is just a much faster, sharper way to communicate exactly what's happening.
But hold on a second. Let's look a bit closer at that chemical formula we just wrote down. Mg plus O2 yields MgO. Count the atoms with me. We have 2 oxygen atoms sitting there on the reactant side, the left side. But over on the right, on the product side, we only have 1. If the number of atoms of each element is not the exact same on both sides, well, the equation is unbalanced, because the mass is not the same on both sides. We call this a skeletal chemical equation. It gives us the basic bones of the reaction. It tells us who the players are, but physically, mathematically, it's incomplete. We absolutely have to fix this.
And that leads us perfectly into Section 3, balancing the scales, the rules of grammar.
You see, the universe operates under a very, very strict rule called the law of conservation of mass. This law states that mass can neither be created nor destroyed in a chemical reaction. You can't just magically spawn new matter, and you can't just delete it into the void. This means the total mass of the elements present in the products has to be absolutely perfectly equal to the total mass of the elements present in the reactants. In simple terms, the number of atoms of each individual element has to remain the exact same before and after a chemical reaction. The universe demands balance, period. And that's why, as scientists, we have to balance our skeletal equations so they reflect actual reality.
Now, sometimes nature's nice and hands us a balanced equation right from the start. Take the reaction of zinc and sulfuric acid. Zn plus H2SO4 yields ZnSO4 plus H2. If we literally just tabulate the atoms, zinc, hydrogen, sulfur, and oxygen, we see that they are identical on the left-hand side and the right-hand side. Check it out. 1 zinc on both sides, 2 hydrogens on both sides, 1 sulfur on both sides, and 4 oxygens on both sides. Because the number of atoms of each element is already identical, this is a perfectly balanced chemical equation right out of the gate. No extra work needed.
But what happens when it's not balanced? Let's tackle a notoriously tricky example together, using what's called the hit and trial method. It's basically like solving a logical puzzle. We're looking at iron reacting with water to form magnetic iron oxide and hydrogen gas. The skeletal equation is Fe plus H2O yields Fe3O4 plus H2. Okay, step 1. Draw boxes around each formula. This is absolutely crucial because you cannot change anything inside the boxes. You can only add multipliers outside of them. Step 2, let's list the atoms. We've got 1 Fe on the left, but 3 on the right. 2 hydrogens on the left, 2 on the right. 1 oxygen on the left, but 4 on the right. So, clearly unbalanced. Step 3 is the trick. Always start balancing with the compound that contains the maximum number of atoms. Here, that's Fe3O4, and specifically, we're going to target its oxygen. To balance those 4 oxygens on the right, we simply put a coefficient of 4 in front of the H2O on the left side. Okay, oxygen is fixed, but wait, step 4. By adding that 4, we now have 8 hydrogens on the left side. So to fix that, we put a 4 in front of the H2 on the right side. Hydrogen is balanced. Step 5. Finally, we balance the iron. We need 3 Fe on the left to match the right, so we place a big 3 in front of the Fe. Step 6. Verify the whole thing. 3 iron on both sides, 8 hydrogens on both sides, 4 oxygens on both sides. Our final, perfectly balanced equation is 3 Fe plus 4 H2O yields Fe3O4 plus 4 H2. See? We just solved the puzzle.
Now, to make our chemical grammar perfectly descriptive, just balancing the atoms isn't quite enough. We also need to know the physical state of the reactants and products. Are they wet, dry, floating away? We use notations for this, a little S for solid, L for liquid, G for gas, and AQ for aqueous, which just means it's a solution dissolved in water. So that balanced iron equation we just did becomes 3FeS plus 4H2O G yields Fe3O4S plus 4H2G. And notice the G right next to the water? That's really important. It specifically tells us that the water being used in this particular reaction is actually in the form of steam, not liquid water. Sometimes we even add specific reaction conditions, like the temperature, the pressure, or any catalysts we used, right above or below the arrow. Like writing sunlight and chlorophyll on the arrow in the equation for photosynthesis. It just adds so much context.
Moving right along to Section 4. Combination reactions, the first genre of literature.
A combination reaction is beautifully simple. It's exactly what it sounds like. It's a reaction where a single product is formed from 2 or more reactants. Think of it as building things up from scratch. A classic textbook example is taking a small amount of calcium oxide, which is also known as quicklime, in a beaker and then slowly adding water to it. It reacts so vigorously to produce calcium hydroxide or slaked lime. The equation is just CaO plus H2O yields CaOH2. That's 2 reactants combining to form a single, brand new product. Other really simple examples of this include the burning of coal, where carbon and oxygen combine to form carbon dioxide, or even the formation of water itself from hydrogen and oxygen gases. You know what I genuinely love about this topic is how it connects directly back to our everyday lives. Remember that slaked lime we just created? A solution of it is actually used for whitewashing walls in a lot of places. When it's applied, the calcium hydroxide reacts incredibly slowly with the carbon dioxide gas that's just naturally floating around in the air. Over the course of 2 to 3 days, it undergoes this slow combination reaction to form a super thin layer of calcium carbonate on the walls, giving them this beautiful shiny finish. And here is a fantastic fun fact for you. Calcium carbonate, CaCO3, is actually the exact same chemical formula for marble. So by whitewashing, you are essentially coating your walls in a microscopic layer of real marble. How cool is that?
So a super crucial point to remember here is that during a lot of these combination reactions, like the slate-lime one we just talked about, a really massive amount of heat is evolved. It gets hot. Reactions in which heat is released along with the formation of products are called exothermic chemical reactions. Burning natural gas, that's exothermic. The decomposition of vegetable matter sitting in a compost pile, exothermic. But perhaps most importantly, the simple act of respiration is an exothermic process. The carbohydrates in the food we eat are broken down into glucose. This glucose, C6H12O6, combines with oxygen in the actual cells of our body to form carbon dioxide, water, and crucially, the energy that is keeping you and me alive right now. It's all just one big life-sustaining exothermic reaction.
Okay, let's jump to Section 5, Decomposition Reactions, breaking things down.
So, a decomposition reaction is literally the exact opposite of what we just learned. It's a reaction where a single reactant breaks down to give 2 or more simpler products. Instead of building things up, we are tearing them down. We are breaking chemical bonds apart. And to do this, to break those bonds, we have to supply energy into the system. And we could do that in a few really fascinating ways.
Let's see exactly how this works across 3 amazing experiments using heat, electricity, and light as our energy sources. First up is thermal decomposition, using heat. If you take some green ferrous sulfate crystals in a boiling tube and heat them up over a burner, they actually lose their water, physically change color, and break down into solid brown ferric oxide, alongside sulfur dioxide and sulfur trioxide gases. You can actually smell it. It has this incredibly characteristic, harsh odor of burning sulfur. Another really vital thermal example is heating limestone, which is calcium carbonate. When heated, it breaks down into quicklime, which is absolutely essential for manufacturing cement globally. And if we heat lead nitrate powder, we get to witness the emission of these striking brown fumes of nitrogen dioxide. All of that just from adding heat. Second, we can use electricity. If you set up a simple electrolysis apparatus, like taking a plastic mug, dropping in some carbon electrodes, and hooking it up to a 6-volt battery, passing an electric current straight through water physically rips the H2O molecules apart. It generates separate, distinct bubbles of pure hydrogen and oxygen gas right there in your inverted test tubes. And third, we can use light. If you take a little white silver chloride powder in a china dish and simply place it in a sunbeam, the light energy alone decomposes it. The white powder literally turns gray right before your eyes because the light is breaking it down into pure silver metal and chlorine gas. Silver bromide behaves the exact same way, which is actually the fundamental chemistry behind old-school black and white photography.
Wow, okay. We have covered immense ground today. We've learned the physical signs of a chemical reaction, we learned how to write them down efficiently as equations, we explored the universal law of conservation that strictly forces us to balance them, and we told the stories of both combination and decomposition reactions. You now officially possess the fundamental grammar of the universe. So I want to leave you with this final thought. Look around you right now, wherever you are, whether it's a rusting nail on a fence, a boiling pot of water in the kitchen, or literally just the breath filling your lungs in this exact second. What chemical reaction is happening right in front of your eyes? Thank you so much for joining me on this explainer, and definitely keep observing the amazing hidden chemistry of your world.